In this video, we prove the permutation lower bound and the sorting lower bound in the IO model. The problem is the following. We have an input of n elements in some order, and we are also given a permutation pi of these n elements. The permutation could be given implicitly or explicitly. And now we want to place these n elements in the order given by pi. For example, if this is the elements, the permutation pi could specify this permutation, where, for instance, the gray circle is placed here, the red circle is placed here, and etc. In the internal memory, obviously this is a very trivial problem because we could just simply write a for loop and place every element where it needs to go. For instance, we could write a for loop, place this blue square over here, place this gray cross over here, and etc. However, in the IO model, the problem is no longer so easy. And here we will prove a lower bound showing that this problem cannot be done as fast as it can be done in the internal memory. So to be able to prove a lower bound, we need to go over the assumption and the model of computation. We assume the elements are stored in a small n blocks, which is capital N divided by B. We assume the elements are atomic. In other words, we can only copy or move the elements. We cannot create elements. We cannot split elements or, for instance, write half of the bits of the elements in this block, the other half of the bits in this block. Informally, you can treat elements as individual items where you can only move them around and not copy or create them. This in particular means that every output item that you produce in your final permutation can be traced back to exactly one unique input item given to us at the beginning. We also assume that the memory size is M and all the shuffling, copying, and moving can only be done inside the main memory. And finally, we only count the number of IOs performed. We do not care about how you store information or how you do computation. Another way of saying this is that information and computation is free. We assume the algorithm has infinite information and it can also do any amount of computation for free. For example, the algorithm could start in this configuration where we have an input of many elements. You can assume each one of these cells is one block. What the algorithm could do is to read a bunch of these blocks into the memory. It could shuffle the elements in the memory for free, and then it could write them back to the disk using IOs. The only thing we care about, or the only operation that we charge the algorithm for, is the reading of the blocks and the writing of the blocks. And thus we can now express the lower bound that we'd like to prove. We would like to show a bound on the number of operation reads and write that we need to do in order to solve the permutation problem.